coordinate systems and frames. Until now, we have been able to work with geometric entities without using any frame of reference, such as a coordinate system. We need a frame of reference to relate points and objects to our physical world. For example, where is a point? We can't answer this without a reference system. The same point can be represented in its world coordinates or camera coordinates. Which one is correct? If you are to represent this vector, is this coordinate system correct or is this coordinate system correct? Well, both are correct because vectors represent directions and they do not have fixed location. These three vectors are just joined at their origin. These vectors are exactly the same vectors. They're pointing in the same direction except that they're originating from different points. So to represent a vector, we can have a coordinate frame or a coordinate system that does not have a reference point. Consider a basis set of vectors v1, v2 to vn. A vector w is written w is equal to alpha 1 v1 plus alpha 2 v2 and so on until alpha n vn. The list of scalars alpha 1, alpha 2 to alpha n is the representation of w with respect to the given basis. We can write the representation as a row or column array of scalars like this: alpha 1, alpha 2 to alpha n transpose, or write it as a column vector. We can also use square brackets rather than parentheses, so we can treat vectors as matrices having just one column. For example, let v is equal to 2v1 plus 3v2 minus 4v3. If v1 is equal to 100 transposed, this sign is for transpose. That means rather than writing this vector vertically, we write it horizontally and put a transpose sign here. v2 is equal to 010 transpose and v3 is equal to 001 transpose. We use the transpose sign for ease of writing, so we don't have to write in columns and we can write as we write normal English in rows. The representation of this vector would be then alpha is equal to 2, 3 and minus 4, again transposed. Note that this representation is with respect to a particular basis, the basis being defined with v1, v2 and v3. In a given three-dimensional space, we can define multiple coordinate systems. For example, here these black lines show one coordinate system and these blue lines show another coordinate system. Coordinate systems, say in a three-dimensional space, are represented by three orthogonal vectors. A different coordinate system could be represented by another set of three orthogonal vectors. We also call these orthogonal vectors as bases, and these two are then called bases, as a plural of basis. Now each basis vector in the second set can be represented in the terms of the first basis. Consider these equations. u1 is the first vector from this basis, and we have represented it as a linear combination of v1, v2 and v3. Hence we are representing u1 with respect to this coordinate basis, and the same goes for u2. We are representing here u2 with these coordinate bases. So here we have a linear combination of v1, v2, v3, and it's a different linear combination that represents u2. In a similar way, we can represent u3. Now these weights, the linear combinations in which v1, v2 and v3 are combined to define u1, u2 and u3, we can put them all in a 3 by 3 matrix M. Now this matrix M relates the v coordinate basis to u coordinate basis. If we multiply M with v coordinate basis, we get this u coordinate basis. You can write this in matrix notation as u bold is equal to m v. The bold sign is that this is a vector, and the uppercase here refers to the fact that M is a matrix and V is again a vector, hence it's a lowercase, and it's bold because this is a vector. So basically, if we have a three-dimensional space, we can define any coordinate system in that space, and we can define multiple coordinate system, but we have to first define one coordinate system and then stick with that, and we represent all our objects and light sources and camera in that one coordinate system so that we can produce graphics images that are consistent. Now in the previous slide we looked at how we can change one coordinate system to another coordinate system by using a transformation matrix M, which was a 3 by 3 matrix. Now we are looking at a vector W which is defined in one coordinate system, and now we want to change it to another coordinate system. Here W is defined in the coordinate system V. Here W is defined with in the coordinate system U. We can write the representation of W as A is equal to alpha 1, alpha 2, alpha 3, because although these two are the same vectors, they are defined with different representations, so hence we call them A and B. And we can write the same vector W as the collection of alphas multiplied by V, because these alphas are the linear weights in coordinate system V that would produce W. Or we can also write W as beta transpose U, where beta refers to these beta 1, beta 2 and beta 3, and they are being multiplied with the vector U, which is a collection of U1, U2 and U3. So here we are basically learning vector notations and vector and matrix multiplications so that we can transform a given vector from one coordinate system to another coordinate system. And in the same way we can transform one coordinate system to another coordinate system. There is a complete set of lectures on coordinate system transformation, so we'll be repeating this a few times more, and if you haven't fully understood this, there's more to come. And it would be helpful if you draw this on a piece of paper and try to understand the transformations, and if you and basically write the equations and practice them yourself. This slide continues our explanation of change of coordinate systems. W is defined as B transpose multiplied by U, one coordinate system, and it can also be written as B transpose multiplied by M and then multiplied by the other coordinate system, because this M relates this coordinate system with this coordinate system. So we are basically replacing U1, U2, U3 with M, V1, V2, V3, and 2 slides behind you saw this relationship that U and V were related by this with this M matrix, and hence we are simply replacing this with M multiplied by this. And now here we are replacing B transpose M with A transpose, which means that A is equal to M transpose B, or A transpose is equal to B transpose into M. Once we transpose two vectors or a matrix and a vector, their order in multiplication changes, because matrix multiplication has to obey the rule that the columns of the first matrix must match the rows of the second matrix. And our relationship B is equal to TA also holds where T is equal to M transpose inverse. Here is an exercise for you. Suppose we have a vector W whose representation in some basis is given by the vector A, which is 1, 2 and 3. Your task is to represent this vector in a new basis that is defined with U1, U2, U3, which are given with these equations. Now remember, we have been talking about vector representations. For vector representation we only need 3 orthogonal directions to define our coordinate system. We do not need a reference point, but to be able to define a point in a coordinate system we also need a reference point to start from. So the convention to represent such a coordinate frame is to have an origin which we call as 0, 0, 0, that is our reference point, and then we attach all the three orthogonal vectors to this origin, and that defines our coordinate frame.